Okay, so hello again, everybody. I want to start today by reminding you one of the last things we did last time, which was to show that this series, this is the alternating harmonic series. I wrote it here explicitly, and it converges by what we called Leibniz test, namely, it's alternating signs times 1 over k, and 1 over k is a sequence that goes to 0, is monotone decreasing, and is positive. So that was precisely the Leibniz test. And I wrote here that, in fact, one can show we didn't do it, but it's a known fact that the sum of this is ln of 2. The only thing we argued was that this sum was something between 1 and 1/2. We said it's 1 minus a half plus a third minus a fourth plus a fifth. Remember we did that? We said that? So it's something between 1 and 1/2, and more accurately, it actually is ln of 2. Okay, so this is where I want to pick up now with a theorem. This is the shortest phrasing of a theorem we're going to see in this course. Well, you shouldn't be that surprised because we already proved that 0 equals 1, remember? So saying that 2 equals 1 is, well, let's prove it. Okay, Therefore 0 equals 2. Yeah, that would be a corollary. Okay, so proof 2 times this thing. So I'm going to write it 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus 1/6 plus 1/7 minus 1/8 plus I'm out of board. That's when the dot, dot, dot comes in. So what is 2 times this number? This is a number, right? Okay, it's ln of 2, but that's a secret. We didn't prove that yet. But this is a number. Do you agree? So 2 times this number equals, well, I'm going to multiply all of these by 2. So what do I get? I get 2. 2 times 1/2 is 1. So I have minus 1. Plus 2/3. Minus 2/4, which is minus 1/2. Plus 2/5. Minus 2/6, which is minus 1/3. Plus 2/7. Minus 2 over 8, which is minus 1/4, plus, and so on. Dot, dot, dot. Oh, we don't have to put that because we already inserted a 2 in. Good? Now this equals, so this equals this equals this. So 2 minus 1 is 1. Minus 1/2. I'm skipping this for a second, so minus 1/2. Now, do you agree that once I use this minus 1/2, there are no more fractions here, even in the dot, 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 that would have 2 in the denominator? Do you agree? Because I can only have a 2 when something here started off with 4 or less, because I'm multiplying by 2, and that's it. They're all bigger. Do you see that? Okay, now let's use all the ones that have 3. So there's 2/3 minus 1/3, which is plus 1/3. And there will be no ones further down that have a 3 in the denominator. Do you agree? Now here's the minus 1/4, and there will be no more that have a 4 in the denominator. And then there's going to be a 2 over 5 here, but there is going to be a minus 1 over 5 coming from 2 times minus 1 over 10. Do you agree? So it's going to be 2 over 5 minus 1 over 5. So it's plus 1 over 5. Minus, there's going to be a 1 over 6 coming from 2 times 1 over 12, and that's the only one. Dot, dot, dot. Good? Was it clear what I just did? Okay, but what is this thing? This is this number that I started off with. Now this number, which is written here as a series, call it x for a second, well, I told you what it is, but even if you don't know what it is, we did show that it's a number between 1/2 and 1. So in particular, it's not equal 0. So if we call this number x for a second, call this thing x, it's this. So what we just showed was that 2 times x equals x, where x is not 0. And since x is not 0, we can divide by it and conclude that 2 is equal to 1. Questions? Yes?
So we just proved
Wait. He's asking. Yeah.
that 2 equals 1, right?
Yep, we just proved that 2 equals 1, right.
Using the Leibniz?
Well, the fact that this infinite series is actually a number is encoded in the statement that this thing converges. Okay, because I can write a series which will diverge, and then writing it would not be a number. It would be just something written. Okay, but this is an honest number. Okay, and we proved that it converges last time using the Leibniz theorem, which we didn't prove, but one can prove.
So why can't we say that showing that 2 equals 1 is a disproof of that? You get what I'm saying?
Nope. I don't understand the question.
Like, we just proved something not reasonable, really.
Yeah.
You're saying this is not reasonable?
Not reasonable.
So how do I...
Not reasonable? No, come on. We're sitting here for already, what, like 3 months, and we're talking rigorous math, and we're writing statements, calling them theorems, proving them. I just wrote a statement, called it a theorem, proved it. That's what's not reasonable about it.
We're using something, a tool, right?
Not a tool. I proved it using a fact that we proved last time.
But to me, that's a fact. 2 equals 1 is not...
Now 2 equals 1 is a fact, right. From now on, you can use it freely. It's a fact. It has just been proven.
So if we find an equation where we have 2, can we put 1?
Yeah, when you have 2, you can put 1. Seriously, I just proved it. Look, do I look laughing, smiling, not serious? Do I look like a not reasonable person to you? No, good.
I'm not laughing either, though.
Hush.
No, but you didn't really understand.
He's not happy. The dude's not happy. Why aren't you happy? You should be happy. You should be happy.
I'm not, but...
Okay, you're saying something's fishy here.
Yeah. Also, before
Well-
I'm just...
Wait. Yeah, so if you're saying something fishy, you have to tell me what did I do that's fishy. Okay. Ahmed, you're so. I confess. Here, I confess. I lied. There's a lie here. Okay, Rebecca, 2 is not equal to 1. Calm down. Oh boy. Okay, so where's the lie? And I promise you the lie is not in this fact or in this fact, because we didn't prove Leibniz theorem, that's true, but Leibniz theorem can be proved. It's not hard, we're just not providing all the proofs. So this is true. Okay, this thing does converge, and it is a number which is not equal 0, and it is ln of 2, but still something here was not kosher. Something here is fishy. Any suggestions? Any more said, yeah, I can see you, but I want to let other people think too. Yeah?
You multiplied something infinite by something finite?
No, I didn't multiply something infinite by something finite. I multiplied something finite. This is a number, because this thing converges, by something finite. It's 2 times this number. It's 2x.
You're always 1 term behind.
What do you mean I'm always 1 term behind?
Because your first term is 2 times 1. So 2 minus 1.
That's this.
And then
Each term here, when I multiply it by 2, is accounted for here. And each term here is accounted for here.
if you look at it on a finite
But I'm not looking at a finite. There's this dot, dot, dot here. And of course, if I remove the dot, 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 everything would be completely false.
So you have on the top one you have n, and here you have n plus 1.
No, I have infinitely many terms here and infinitely many terms here. And they're precisely the same terms. Precisely. There's what? 1 here, and here it is here. And there's a minus 1/2 here, and here it is here. And there's a 1/3 here, and here it is here. I didn't skip anything or leave anything out.
First term is 2.
Here? Yeah, but 2 minus 1 is 1.
That's already your first 2 terms put together.
Because I added them up.
No, but when he's saying that on the infinite term, you're going to be 1 back.
No, when you have infinitely many terms, you can't say I'm going to be 1 back. Okay? I have each term here, the precise statement is the following. Each term here is accounted for here and vice versa. I agree that there's a 2 minus 1 here, but here it is. I agree that there's a 2/3 minus 1/3 here, but here it is. Okay? There's nobody here in the dot, dot, dot left out here. And there's no term here that I just imagined from nowhere. Each term appears precisely. Any other suggestions? Ah, your hand is down now?
No. I'm just awesome. I'm not sure about that, but I have 2 things. The first thing is it is like we're dividing one series by another series.
No, we're not dividing.
Oh, and 2x equals x. When we say that x is equals to the series.
X is this number. This thing is a number. Once we say a series converges, it means that it's a number. We argued that it's some number between 1/2 and 1. I even told you just now what it is more precisely, but it's a number. And I showed you that 2 times this number equals this number. If it were 0, then this wouldn't say too much, but it's not 0. Okay. The lie is here. Here's the lie. The lie lies in this equality. So this is false. This thing is... I like how people take credit. I was right. Yeah. False. In other words, it's a lie. So why? What's wrong here? What's wrong here is that I used properties of numbers that are true for numbers. They are true for the field of numbers called R with a double leg, the real numbers. Namely, 2 laws that I used here. One is the Associativity Law, saying that when you have an addition of things, you can add them in whichever order you want and you get the same thing, right? And that's true for numbers. If you have A plus B plus C, that's the same as A plus B plus C, and that's the same as A plus C plus B. They're all the same, right? So that's 2 laws. That's the associativity, which tells you the order doesn't matter, and which tells you the order of the parentheses doesn't matter, and the commutativity law, which tells you can swap the direction in which you're adding. A plus B is the same as B plus A, right? And that's what I did here. I did both of them. And both of them are not true for infinite sums. So when I said 2 minus 1 equals 1, that's true. When I said 2/3 minus 1/3 is 1/3, that's true. But doing it in the dot, 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 doing it on the entire thing is already false. I cannot just change the order in which I add the terms, which is what I did in passing from here to here, right? I moved the minus 1/2, I moved it here. Do you see it? And I first added these 2, then I moved the minus 1/2, then I added these 2, and then I moved this over to here. Do you see that I use these 2 properties again and again and again? And that's false. You can't do that in series, in infinite sums. How do I know it's false?
Do 1 minus 1 plus 1 minus 1.
No, I know it's false because if it were true, then this would be true.
And intuitively, you know how to explain why?
This is precisely it.
No, I can see that I cannot use that, but I want to know intuitively why, if it's possible.
So intuitively, why what?
Why I cannot change the order of what we're talking now.
Okay, good question. Well, first of all, usually you need to know why something is true intuitively. Okay, so something is not true until you understand why it should be true. Okay, so what we're doing here is taking a property that we know should be true for real numbers and trying to extend it to series. Okay, and that's just, there's no reason for it to be true. So that's the first statement. I think this is very convincing as intuition to why it is false. You can play with other numbers. So you can like take things with pluses and minuses and try moving all the pluses to the beginning, so you'll get a number bigger and bigger and bigger and bigger and bigger and bigger. You'll never get to the subtracting part, right? So something like +1 -1, which actually doesn't even converge, you can make it suddenly go to infinity or do all kinds of funny things. So I think that the fact that the intuitive intuition that you can do things like this is rather simple. It's just false. And in particular, it's false here. So let me write this. Let me write the statement. So the theorem is that, okay, it has two parts. If this is part of a much bigger discussion which I'm not going to go into. I'm just really touching the tip of the iceberg here. But that's all I'm going to say about this. But I think it's important to remember. If a series converges absolutely, which is not the case here, right? The harmonic series was our first example of a series that does not converge absolutely, right? In absolute value, sorry, the alternating harmonic series in absolute value is the harmonic series which diverges. So this is not the case here. But if it were the case, then any series obtained from it by changing the order of summation so just summing them up in a different order, whatever order you want, would also converge absolutely to the same sum. So if you're in the realm of absolutely converging series, doing moves like this is completely kosher. It's fine. Okay? However, and this is what we learned from this example, if sigma an converges conditionally, namely it converges but in absolute value it doesn't, so this is where then by changing order of summation, you can make it converge to any number in the world you want, to any sum, or you can even make it diverge. So you can really do wonders. Proving these is not hard, but again, I'm not gonna spend time on them. We're really pressed in time in this course. But the basic idea here is that you can take all the pluses or take enough pluses to exceed something and then take some minuses and then go on. do things like that. If somebody's interested and wants to talk more about it, later, not now. Okay? Okay. There's I'm not even going to write it. There's a similar sort of theorem regarding what we called associativity, when you can introduce parentheses, when you can take out parentheses, which is also something we did there, and is also in general false, and under certain conditions it's true. Okay. Later. More stuff about this during the break, okay? I really have to move on. I want to do one more example. And this is the following example. Sigma n equals 1 to infinity minus 3 to the power n times n factorial divided by n to the power n. Lots of n's here. So the first maybe when you see something like this, the first thing you may think of would be this is Leibniz-ish, right? Because there are alternating signs here. Do you see that? So then you can say, okay, for it to be Leibniz, you rewrite it as minus 1 to the n times 3 to the n. Minus 1 to the n is the Leibniz part. And then you have to take the entire remaining part, 3 to the n, n factorial over n to the n, and show that it's monotone, decreasing, tends to 0. Well, obviously it's positive. Okay? That may or may not work. Okay? May or may not work. And what's sure is that it's not easy. Okay? It's not immediate. I want to show you a different method to tackle this one. And that's the reason I'm putting this example on the board, which is the following. So what I'm going to do is I'm going to see if it converges in absolute value. Okay? And when I put it in absolute value, it of course becomes a positive series. If it's a positive series, I can apply all the various tests that are valid for positive series, and in particular, which is the one which I really want to apply here? Not compare. The ratio test. Whenever you see this factorial, it's really, hey, use ratio test. That's how you can, that's what you should have in mind. Okay, factorials really call for ratio tests. So let's do it. So what's an plus 1 over an? I'm doing the ratio test for the absolute value. So what I get is, oh boy, so it's what? It's 3 to the n plus 1 times n plus 1 factorial divided by n plus 1 to the power n plus 1. And I'm multiplying by the reciprocal. We did that a few times. The reciprocal of an instead of dividing. So I get 3 to the n factorial. Right? Everybody good? Say yes.
Yes.
Thank you. And now all the cancellations, which I'm going to do in a way that I don't want you to do, because it's only good when you see it showing up. So this 3 to the n cancels with the n plus 1 here, leaving just a 3. Do you agree? This n factorial cancels with factorial, leaving just an n plus 1. Do you agree? Now this n plus 1 here cancels with the plus 1 up here, leaving just n of them. Good? So what I'm left with, after doing this, and please don't do that, is 3 times n over n plus 1 to the power n. What do you smell? E. Good. So I'll rewrite this as 3 times 1 over n plus 1 over n, which is 1 plus 1 over n to the power n. And as n goes to infinity, this goes to what? To 3 over e. Now e is what? 2 point something, so 3 over e is greater than 1, therefore, so the conclusion at this point is that sigma an in absolute value diverges by the ratio test. Does it imply that the original, that sigma an itself diverges? No. Remember, sigma an converges implies that sigma an without the absolute value converges. That's being converging absolutely. But if this diverges, it does not imply that without the absolute value diverges. The example is, for example, the alternating harmonic. Do you agree? So did we gain any further insight by doing all this? Seemingly not. Okay? But in fact we did. And the reason is, I wrote here a reminder from something we also saw last time, and it's the following. We didn't prove it, but we said it. If a positive series diverges by the root or by the ratio test, the root and the ratio test in divergence can only pick up series where the sequence doesn't even go to 0. Remember we said that? Okay, so they're weak in picking up diverging series, and we showed it on examples even. Okay, whenever they picked up something diverging, it was really diverging for the most fundamental reason that the sequence doesn't even go to 0. So in particular, if this diverges by the root or ratio test, then this doesn't go to 0. Do you agree? But if a sequence in absolute value doesn't go to 0, hence an itself doesn't go to 0. Because these two are if and only if. Right? If an goes to 0, then in absolute value it goes to 0 and vice versa. So if it doesn't, this doesn't either. And therefore, sigma an itself diverges. Clear? So if you take a series, sigma an, look at its absolute value, and apply the root or the ratio test, if they converge, this converges. That's straightforward. That's the statement of being absolutely convergent. If they diverge, this diverges too because of this argument. So it's only true if you found out the divergence using the root or the ratio test. Only if you used this. Clear? So back to our example, we found out that this diverges by the ratio test, and therefore this diverges as well, because of the previous argument. Okay? And I want to just say one little detail here. This is an interesting example. If we replace this 3 with a 2, write a 2 instead of this 3, and run everything the same. So there will be a 2 here and the 2 here. The cancellations would be the same. You'd get a 2 here. You'd get a 2 here. But what about 2 over e? 2 over e is less than 1, and therefore this converges, and therefore this converges absolutely, and therefore this converges. Do you see that? So if you were to look at this, with all these n's around, the factorial and the n to the n and everything, you would think that the thing that has the least impact would be if this is a -3 or a -4 or a -2. That shouldn't really make a difference, but it does. Okay, that's again to exhibit how delicate this thing of being a convergent series is. Okay, intuition, don't ask me. Okay? You can get intuition in general, but for the delicate part, too delicate. So if you put a 2 here, it converges. And where would the threshold be between... Right, if you put an E here, the limit here would be 1, and the ratio test would fail, and you'd have to do something completely different. Okay, but any number less than E would converge, greater, less than is not the right. Greater than E minus would be converging, and less than E with a minus I would be diverging. Good?
It's possible to repeat that part, or you know?
What, this statement?
Yes. No, the reason that this is divergent also when it's not absolute value.
Okay, so you have to trace the facts here line by line. There were a bunch of them. Okay, so if any of them weren't clear, I'd be happy to discuss it later again. Okay, but the bottom line of this entire statement was that in fact you can use the ratio and the root test on series even if they're not necessarily positive. Okay, you can put them in absolute value, apply the ratio and the root test. If they happen to work, the conclusion holds for the original series as well.
And if the absolute value converges, also the number one will be...
Well, if the absolute value converges, then it converges absolutely, and of course it converges without it, right? That's always true with or without the root or the ratio test. Whatever you use, that would be true. Okay? Okay. My final comment regarding series, and then we'll move on to power series, which is our last topic for this semester. So the final remark I want to make is that there are more theorems and convergence tests. We don't have time, and this course is really not doesn't encompass the whole subject in every detail. So there are more convergence tests, some of which are very powerful. Let me write e.g., and I'm not going to even spell them out, I'm just going to give you their names and you can look them up if you're interested. There's what's called the Abel test, and there's one called the Dirichlet test, same Dirichlet from the famous function. I'm not going to spell them out. You can look them up if you're interested. I'm really only saying this so you know that they exist. And if you somehow, I mean, these things will show up in real life, depending on what your real life is. But in engineering, these things show up, and that's where you guys are mostly headed, and in other sciences. And I just want you to know they exist. Both of these are powerful in the sense that they do not require positivity. They work for any series, and they don't require, they discuss products, sigma A and Bn, things like this, and you don't require both to converge. You require weaker things, but that's all I'm going to say at this point. So this wraps up the topic of series for us. Let's have a break now. I know this was short, and the next hour will be longer, and then we'll continue with power series.
But the tools that we have to find if converges or not.
Please, wait for it to go blue, then ask. Okay? Yes.